Hi everyone, welcome to my presentation. My name is Dongping, and today I'll talk about our recent work, surveillance evasion through Bayesian reinforcement learning. Starting with the problem setting, we consider a 2D continuous path planning problem, where an evader is trying to escape a region under the surveillance of some observers. We assume that the surveillance intensity is this positive smooth function k of x, which determines how likely the evader might be captured. Here I'm showing you one example of this function k. The probability of the evader being captured along a path y before time t takes the following form. And you may observe that it monotonically depends on the integrated k value along the path. This is the quantity that the evader wants to minimize. Once we understand that, we realize that this task falls into the standard optimal control framework, where we can solve a corresponding PDE and obtain the path with the minimum capture probability, as is shown in the second figure here. Now, let's consider a more realistic situation, where the evader does not know the surveillance intensity k. Instead, he needs to conduct the task of evasion for a certain number of episodes, gradually learn the function k, and in the meantime try to reduce the capture frequency as much as possible. We assume that the evader restarts at the same location every time. This now becomes a reinforcement learning problem. On the right figure, I'm showing you the simulation results of one of our proposed algorithms. The magenta dots are the locations where the evader was captured. The black curve is the finally predicted optimal path. In the background is the predicted intensity. There are two main challenges here. One is how to select a good model to reconstruct the function k. Another one is how to strategically learn the function k on those relevant parts of the regions, while making sure that asymptotically the optimal path can still be found. I'll explain how we deal with these challenges. Before I show you any algorithms we propose, let's first take a look at how we can adapt an existing RL algorithm, the upper confidence bounds on trees, to apply to our problem. So this algorithm can be viewed as using confidence bounds as guidance to Monte Carlo tree search. It is applied to an MDP version of our problem by adding a capture state. A unit cost is induced whenever the evader is being captured, or in other words, it transitions into a capture state. This is the model-free method, and it directly attempts to learn the state action values. For example, suppose the evader starts at the cyan dot here. It selects 5 paths, all following this edge E sub 1. Among 5 trials, 3 times he got captured, shown by these red dots, and 2 times he escaped, shown by these green paths. Then the state action value QE sub 1 is estimated as 3/5. Either the unit cost of being captured or the zero cost of escaping are backpropagated to update the state action values of each node along the path. At each node, the algorithm selects the next action as the argmin of this quantity, where n sub v and n sub e are visit times of node v and edge e. It can be viewed as a confidence bound of this estimate, and this type of modification plays a key role in strategic learning and will appear several times in this talk. Although we can obtain the convergence of state action values if we take infinitely many past samples following an edge, this is much less efficient. The reason is as follows. When a capture happens, it is penalized along the path backward in the same way for all nodes. This is less reasonable because the early state action values should not be strongly affected by a capture which can be further away along the path. UCT ignores the possibility of using the capture and non-capture data to build up model estimate locally on each edge. We do not expect any model-free methods to perform well, and all of our proposed algorithms are instead model-based. Our first attempt is to set up a graph version of our problem by introducing an edge capture probability and converting it to an edge cost, phi sub e. Let phi sub e tilde be the estimate of phi sub e using historical data. The algorithm, named as ALG-D, solves a shortest path problem in each episode, based on not just phi e tilde, but phi e tilde minus a term which is proportional to the standard deviation of this estimate. Again, this is a confidence bound type modification. Once we found that shortest path, we simulate running through it and update statistics for future episodes. Although we can prove a 1 over square root of total episode bound for this algorithm, the actual performance of this algorithm is not as promising. One obvious issue is that ALG-D updates each edge estimates independently, ignoring the phi sub e cost correlations between near edges. Another one is degrees of nodes have to grow in order to obtain all directions of motion. For example, in the following stencil, each node is connected to its 8 neighbors. However, the direction of these dashed lines are missing. And of course, increasing the connectivity of this graph increases the computation complexity. As a result, it's more reasonable to use a continuous model of function k. For example, we can use a piecewise constant model to construct the following ALG-PC. It similarly derives a path and simulates running through it in each episode. But this time, the path is obtained by solving a PDE based on a confidence-bound modified intensity k hat. K hat is constructed in the following way. We decompose the domain into a collection of cells. Assuming that k is a constant, we can obtain estimate of that value within each cell using historical data. Since k is positive and we want to avoid truncation at zeros, we instead model the log of k. That's why you see this exponential function here. Focusing on what's inside the exponential, there are 2 terms. The first term, which is the statistical estimate of log of k value, can be viewed as the exploitation motif. When this estimate is not accurate enough, if the evader selects a plan only according to the first term, it's very likely that he got stuck at some local suboptimal solution and never explore other regions. Therefore, there comes the second term, which is the exploration bonus. It is a constant times the estimated standard deviation of z value. For those less visited regions, z value is not accurate enough, hence sigma z becomes larger, and k hat becomes smaller here, which encourages us to consider going through this region in future episodes. And we expect that these 2 terms can automatically balance between exploration and exploitation. However, there's still a problem. ALG-PC updates the k values in each cell independently, so it still ignores the correlation between cells. A better idea is to use a GP regression, which is known to be able to handle the spatial correlations automatically. We can treat the z tilde and sigma z tilde values from previous slides as inputs of a GP regression at cell centers, which results in our final algorithm, ALG-GP. A kernel function needs to be specified for GP to determine how correlated 2 input points are. One common choice is, for example, the squared exponential kernel, usually under the assumption of smoothness, which is true for our intensity function. Alpha and beta here are hyperparameters which can be inferred from data, and we conduct a tuning every 1,000 episodes. ALG-GP similarly derive this intensity surrogate k hat in each episode. The only difference is it replaced the z tilde and sigma z tilde function by the posterior mean function m and standard deviation function rho, which are derived from GP. And GP regression is the reason why we call it Bayesian reinforcement learning. Now that I've shown you all of our proposed algorithms, let me move on to numerical results. First, I want to show you some simulation results of different intensities using AlgGP. The magenta dots, i.e. the capture locations, give rough indications of which parts of the region AlgGP prefers to explore. And you can infer how often the algorithm explores a part of a region by the density of these dots. Take the middle one as an example. AlgGP mostly selects a path around the locally optimal trajectories, one going upward and by symmetry another one going downwards here. And it focuses more around the globally optimal trajectory. We also tried this example 3 with even more locally optimal trajectories. All of these results show proper balance between exploration and exploitation. And you may observe that the finally predicted trajectory is quite close to the true optimal one. To compare AlgGP with different algorithms, we define a performance metric as follows. Let the capture indicator delta I to be 1 if a capture happens in the ith episode, and 0 otherwise. The performance metric we use is defined as the ratio of being captured up until the jth episode minus W star, which is the capture probability along the optimal path. This is the experimentally observed excess rate of captures due to not selecting the optimal path. And in reinforcement learning language, this is usually called a regret. We run all 4 algorithms for a total of 15,000 episodes for all the intensities I've shown you. And you can observe from the figure, UCT, the purple curve, generates the largest regrets throughout. AlgD, the orange curve, have smaller regrets, but it suffers from slow convergence rate and almost stagnates after 10,000 episodes. These 2 algorithms have theoretical proof of convergence, but their actual performance is not as good. The piecewise constant model, AlgPC, the green curve, is slightly better than AlgD, but the improvement is not significant. The regrets for AlgGP, the blue curve, continuously decrease and appears to confirm the convergence. We also experimented non-smooth intensities, and in addition to the squared exponential kernel, we also tested Martin's kernel, which assumes less smoothness in the interpolated function. For the left example, k is not smooth but still continuous. The squared exponential kernel, the blue curve, still remains the best, although the Martin's kernel, the yellow curve, is almost as good. When k becomes discontinuous in the right example, AlgPC initially outperforms both GP-based algorithms, though eventually Martin's kernel catches up. The good performance of AlgPC in this case is likely due to the fact that the intensity is truly a piecewise constant function. To sum up, we consider a surveillance evasion problem with unknown intensity. Our proposed algorithm applies confidence-bound technique to guide the exploration and exploitation, and uses GP regression to handle the spatial correlations in data, which results in much faster function learning. Also, if you're interested, feel free to visit the following website for more details about our paper. That's all. Thank you.